nobody remembers it because we didn't call it the right name. We should have come up with a cool name for it. So what is microrheology? Microrheology is really a way of using a probe particle. Remember, I said with light scattering, whether it's standard light scattering, any dynamic light scattering, standard light scattering, or it's DWS, diffusing wave spectroscopy, or even microscopy, you can measure the mean square displacement of a particle. So the particle is moving through the medium and it's driven by thermal energy. Normally it just diffuses, but if it's in a more viscoelastic medium, it moves in response to the medium. So here's the correlation function from hard spheres near the glass transition. Here's the mean square displacement that you get from that correlation function. Notice it increases. This is increasing linearly because it's diffusing, and then it approaches a plateau. Remember, we showed the motion of the particles. It approaches a plateau because it's trapped in cages. Then it moves out. Okay, but Tom realized, and he realized this just while he's trying to prepare for the March meeting. He realized that you could replace the description, basically the Stokes-Einstein description. You could replace that with a time-dependent thing, not just something that depends on time, but something that depends on frequency, or the Fourier transform frequency in Laplace space. And from that, you could actually calculate the modulus. So I don't want to go through this. It's a little bit complicated. Since then, a lot of people have worked on it, and there are simpler ways of determining it. It's basically, let's see, the G prime and G double prime are related by the Kramers-Kronig relationship. And so if you measure one, you can measure the other, or you can measure a complex version, which is the sum, the sum of the two of them. So this is really the sum of the two of them. This is the complex frequency or time-dependent modulus. You take the Laplace transforms, and basically you get these curves here. It's exactly what you measure from the rheology. So this just shows that you can actually measure the rheological properties of a material by looking at the motion of the particle. Now, what's the physics of? The physics of this is that if the particle is in a fluid, it's diffusing, right? And if it's diffusing, I know kT and I know the particle size. Therefore, I can measure the viscosity of the fluid. Well, the viscosity is 1/2 of the rheological response. Similarly, if I have a particle attached to a spring, I know that it fluctuates, but it doesn't go anywhere. But it does fluctuate, right? It's got kT of energy. If I attach it to a harmonic spring, it just fluctuates with kT of energy. I balance that kT of energy, that fluctuation, with the spring constant, the energy stored in the spring. I can measure the spring constant. The spring constant is essentially the other half of the elastic medium. So it's not surprising that it reflects the elastic medium. And so, in fact, this has now become a good way of measuring the rheological properties of materials just by tracking particles, by doing particle tracking. OK, let me go back. I showed you this phase diagram. We talked about this. Now I want to try and talk a little bit about the other two. Let me start in here. And talk about colloid aggregation and colloid gelation. So I showed you this rough schematic for the requirement, always the requirement of colloids, that you need to have some energy barrier, some repulsive energy barrier. Sometimes you have an attractive interaction. This is fairly rare. But you have this repulsive barrier, and that keeps things stable. But if you can get rid of this repulsive barrier, I've obviously drawn this out, extended this to a shorter length scale. If you can get rid of it, then you have just an attractive interaction. Well, it turns out that if you work on a more engineering basis with colloidal particles, sometimes they just go bad. They become unstable. And in fact, there are ways that you know that you can destroy the stability. For example, if they're charged on the surface, you can put something into the solution, just mix it up in the solution that either displaces the charged group or neutralizes the charged group, basically gets rid of the stabilizing charge. And then you start getting the colloidal particles to stick to one another. So let's just do a little simple physics and ask what happens. if I take this random suspension of particles and I make them unstable, so they have a size here. I'm going to not be consistent. I'm going to sometimes write A, sometimes write R. Here I've written R for the radius of the particles. This is their diffusion coefficient, and there's some concentration. And I destabilize them. And let's say the concentration, if I take the cube root of the concentration, I get some average spacing. I'll call it S. How can I calculate how long it takes for the particles to collide with one another due to diffusive motion? Because now they're unstable, so if they collide with one another, they will stick together. There's a short range attraction. They'll actually stick. So as soon as they come close to one another, they'll stick together. So I want to look and understand this. So how can I calculate this? How would anybody do that? Any ideas? They're diffusing particles. They have to diffuse a distance S. What's your first thought? Pardon? S over the diffusion constant is not units of time, right? I want a time. So this is what you're saying. S is, it's S squared over D, right? That's the time, right? That's the time it takes for it to diffuse a distance S, right? That's just diffusion. So I can put S as basically the cube root of the, or 1 over the cube root of the concentration. It should go like this. That's the natural thing that you should do. Just how long it takes to diffuse a distance between the particles. That's completely wrong. Why is it completely wrong? Because you don't know if it's going to hit this particle. It's just going to go some distance anywhere. So the right calculation, this is originally done by Smolkovsky. The right calculation is you have to essentially ask how long does it take for one particle to explore the average volume separated by the other particles. Because it's not enough to go here. It has to go everywhere, so eventually it hits a particle. And you can do that. I just did a simple calculation. So the volume that this is a distance now. I've called it R. I apologize. It's really the reason I called this R is if I go a distance R, it's actually gone some length, some contour length, S. And that's S times whatever that length is times the radius of the particle. That's the volume it's explored. And I can figure out this contour length by saying, well, I know the number of steps it goes, and I know the step length. I know what the step length is. I'll just take the radius of the particle. That's as good as anything. And the number of steps is just this divided by the radius, by the step length squared. That's the contour length. And so that gives me contour length. This S is R squared over A. So I'm just going to take R squared over A. I'm still going to have the time. It goes as R squared over D. So now I have the volume over time. The volume is just the inverse of this. So the time now goes not, remember the other was 2/3 concentration. It goes linearly with the concentration times A times D. Actually, if you think about this, A, D, if it's a diffusing particle, D is kT over 6 pi eta A, right? So the A's actually cancel out. It just depends on concentration. So if you do that, what happens is, of course, the first ones, they start to collide with one another, but then the other ones start to collide, and then the dimers start to collide, and then the trimers start to collide, or the quatrimers, they collide, and you get structures that look like this. This is now really early days. These experiments were done with colloidal gold. They were done in the real early days, even before we thought about doing light scattering or any of the kind of techniques. This is just done with electron microscopy. This is an electron micrograph of the images. And eventually they grow, and they grow into these really large structures. But now, here's an interesting fact. These are structures. These are three-dimensional structures, but I'm taking a picture of them with an electron microscope. An electron microscope, it doesn't matter, I prepare the sample, but the way to think about this is I'm taking a picture, I'm looking through the sample. So this is a projection of the sample, right? I'm looking right through the sample. Look at these. I'm looking through something. It occupies three-dimensional space. I'm looking through it, and I can see right through it. Right? That means it's got a really funny structure. So how can you describe that structure? Well, you can take these data, or these data, and you can just measure their size, just measure their radius, and you can measure the mass. You just count the number of particles. That's the mass. and you plot the mass as a function of size on a logarithmic scale. As I said, this was early days. I could tell you another interesting story about this, but I won't. Early days of, so it's a log scale, but you still get a logarithmic correlation. But the slope of this, the mass, how it grows with the size, is 1.75. What does that tell you? That means that the mass is growing, but it's growing not as r cubed, but much less than r cubed. In fact, it's growing less than r squared, right? If the mass was growing as r squared, then I could completely cover the surface. But it's growing less than that. And that's what it has to be. This is a fractal. The mass grows as the radius to some fractional dimension. And that's the key, that why you can see through these things is because it's growing relatively low amount of material so that it has lots of holes in it. And actually, if you go back and look at this, look at the size of the holes. Here, the size of the hole is this. What's this? About half the size of the particle. Here, the size is about of the cluster. The size is about half the size of the cluster. Half the size of the cluster. Half the size of the cluster. The holes are growing just as fast as the particles, right? And they have to, because it has to be a really dilute object. And you can calculate the density, and just as the density, if it's growing as the radius cubed, then the density would be constant, right? But it's growing less, so the density is actually decreasing. It's decreasing. So you can actually look at the correlation function. Just take the correlation function from this and calculate this and measure the correlation function. This is, again, a logarithmic plot. And you see it's falling off in space until the size of the cluster. So this is that same large cluster, just calculating the correlation function. The slope is minus 0.25. You should think that it should be minus 1.25 because it should be the sum of that, and the fractal dimension should be the dimension of space. But this is a projection, so the dimension of space is reduced to 2 dimensions. Well, OK, I can't help but telling you the really interesting story. This was done a long, long time ago, probably before many of you were ever born. And the first IBM PC had just come out. And I had a summer student from MIT who was doing these calculations and doing these experiments. And we did the correlation function on the IBM PC. The IBM PC had 28 kilobytes of memory. It had, we paid twice as much as the computer to have a 10 megabyte hard drive. It took 3 days to do the calculation. So now you have to understand, in those days, if you wanted to make a plot like this, what did you do? Well, of course it's by hand, but this is a log plot, right? So you had to figure out, you had to look through all the data. It's not a computer. You have to go through data by data, one by one by one by one, every data, find the range of the data. Then you go down to the stockroom, and you get the right graph paper that has the right number of decades of log paper. And you plot it by hand, every point by hand. So there's 1,000 points. You do it every point by hand. This is what you did. This is how you did science. You really understood your data when you did that, let me tell you. And if you got the number of decades wrong, boy, you were up shit's creek, because you had to go and get a new kind of graph paper and replot all the data. So this guy, he showed me on the computer. He showed me this plot, but he did it linear. I said, oh, too bad. You got to plot it log. Really. So what do you do? Click, 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 click. What you do now? A couple of clicks. And it turned out to be a log plot. I never in my life had seen that. And that was just an amazing, amazing thing. This was Lotus 123, which, of course, doesn't exist anymore. But that was the first program, the first spreadsheet program, that really made the PCs popular, because you could actually plot these data. So this was plotted. This is the first computer plot of something that I had ever done. Really, the first one almost that anybody had done. Back when you had no idea you could do things like this. So it was very cool. OK, enough reminiscence. what I showed you were structures that look like this. Sometimes you'd see structures that look like this. Now look at this. Can you see through it? Sort of. But over here, can you see through that? Not really. So if you do this, this is still enough that you can do. If you do actually do experiments with these kind of things, and I can tell you the details of how you get that, I will in a second. But if you do this and you measure the fractal dimension, what do you immediately know by the fact that you can't see through it? Higher by how much? More than 2, exactly. It has to be greater than 2, right? Because you're filling a two-dimensional space. So if you're filling a two-dimensional space with something fractal, it has to be greater than 2. And this is greater than 2. This is about 2.1. And so the difference between this is, in the first case, you have the particles actually, whenever they stick to one another, they immediately, or whenever they hit one another, they immediately stick. But if I put a little bit of a stability barrier, so let's say it takes 1,000 times or 1,000,000 times before they actually stick. They're not really stable, but they're quite stable. Then they're diffusing. If they're diffusing, actually you know that if something's diffusing, it only sticks to the outside, even a single particle. It only sticks to the outside. It cannot go in because it's diffusing. And so it's going to explore all space, and it's going to hit somewhere on the outside much more rapidly than go on the inside of these arms. But if it's not, if it doesn't stick, then diffusion can allow it to come in closer. And that's going to lead to a higher fractal dimension. So there's actually several dimensions. You can talk about the Euclidean dimension. Euclidean dimension was 2 for a surface, for two-dimensional space, 3 for real space. The fractal dimension is the amount of volume that you cover, or actual volume. It tells you the mass. And the trajectory dimension is the trajectory of the motion. So there are 3 different types of trajectory motions you can imagine. If it's diffusive, then the trajectory motion, that contour, is behaving like the length squared. If it's ballistic, if it's going straight, then it's 1. And if there's no motion, if it can go anywhere, its dimension is 0. And so, in fact, you can get some sense of what's going to happen by just summing the 3 dimensions, the fractal dimensions of the 2 objects and the trajectory dimension. That's going to tell you something about how things combine together. So in the case of 2 clusters, they have 2 clusters have 1.75 each, and the trajectory dimension is 2. It's much greater than 3. And so that means that you're always going to stick on the outside. You'll never be able to go on the inside. Similarly, even if it's a point particle whose dimension is 0, right? It's just a point. Its dimension is 0. If I sum that, if it's diffusing, it'll never get inside, right? But if it's not diffusing, if the way to think of something that can explore anything, that is, it diffuses but it never sticks, that's like having a no trajectory dimension. Its dimension is 0. Then if I sum this, it would be 1.75 plus 0 plus 0. It's less than 3, so it can go inside. So this is just a way of thinking about, of qualitatively understanding the nature of how things combine and how things structure. And it doesn't tell you the details, but it gives you some sense of the kind of structure that you're going to get. Yeah?
When these clusters are formed, do the arms move around in time?
That's a good question. They do eventually, but they're pretty rigid. These were gold particles, and they were a gold-gold bond, and so they're pretty rigid. So eventually, they'll fluctuate as they get larger and larger. So you can just take KT, you can calculate some bending energy, and you can ask how big they are. Actually, I think that gets me to I did a little calculation. I called it my brown bag calculation because I just had a piece of paper. I just wanted to do this. I wanted to ask a question like that. And so I want to ask the following question. If I have one particle in this room, well, no, let me start with a simple case. I have lots of particles in this room, and they stick together with these random structures, right? Eventually, if I have a finite volume like this, eventually, if there are enough particles here, and they're rigid enough, I can form a rigid structure that spans space. That's a gel. And so I can get gelation of colloidal particles, right? So now I have a question for you. If I have one particle, or if I have a certain number of particles that are going to gel, but now let's take this room, and I'm going to put one particle in this room. Can I possibly form a gel, a solid structure that spans all of space? One particle. One particle. The particle is going to be, in this case, say a millimeter in diameter.
There's nothing else for it.
Nothing else. Probably not, right? OK, but now let me do what the experiment we just did was a finite volume. Let me take an infinite volume, or a much larger volume. Will it ever gel? Just one particle in this room. Will it ever gel? Oh, sorry. What I mean that sorry, I didn't define my hypothesis properly. My volume fraction now is the volume of the particle divided by the volume of the room, right? So a 1 millimeter particle divided by the volume of the room. What's that? 1 in 10 to the 18 or something like that? I don't know. OK. Will it ever gel? He says no. Anybody else want to hazard a guess? Remember, the density is decreasing as I grow these clusters. So I need less and less to fill more and more space. So in an infinite system, it will always gel. It will gel because it'll grow. It may take forever. You may not be able to wait. OK? But let's say we can turn up time so we can wait long enough. And that the particles are solid enough that thermal fluctuations don't play a role. But then it will always gel because you can always fill space. If I have an infinite number of particles, I can always fill space because the density is decreasing. So I need less and less to fill more and more space. So what's going to happen, I've tried to draw that here. What's going to happen is you're going to form clusters. As they get larger and larger, you need less and less material to get more and more volume. And eventually you have, this is meant to represent 3 different clusters. So eventually they're so dilute that they're essentially filling all of space. And they'll gel. So they'll be fractal up to some length scale, and above some length scale, which I called R sub c, so for some critical crossover length scale, here, above that length scale, they're uniform. So remember, as I grow these fractal clusters, I take fewer and fewer particles. So I need less and less material. The density is decreasing as they get larger. So I can calculate this value. This is a simple calculation, right? That's why I did it on this brown bag. So if I want to look at gelation of faster clusters, I can calculate how many particles there are in the cluster whose size is RC. It's just the mass. OK, I'll call them the number. So I divide by the size of the particle. And the radius of the cluster is just that to the fractal dimension. And so this, because this is less than 3, this is growing. It's growing more slowly than space, right? So as I make it larger and larger, I'm filling more and more space. So now I can just calculate, put this in terms of the volume fraction. So the volume fraction, which is the number of particles per volume. OK, the volume is just one of these cubed. Again, I divide by a to put it into unitless numbers. So that's the volume, and this is the number of particles. So this is the volume fraction. This is the initial volume fraction. So I just divide both sides by this. And so the initial volume fraction is this. And so the size that they're fractal to is this. It's the size of the particle times the volume fraction to the 1 over the fractal dimension minus 3. So just think about this. Let's say the fractal dimension is 1.75, 2.1, something like that. Let's say it's 2, because it's easy to do. 2 minus 3 is minus 1. So it's just the volume fraction to the minus 1. If I started with a volume fraction of 10 to the minus 6, which is typical of what these gold colloids were, then it's just the radius of the particle times 10 to the 6th. If it's in this room, right, and it's, we said it's, I don't know, 10 to the minus 18 times a millimeter. So it's a millimeter times 10 to the 18. That's the size you'd have to go before it became uniform. But it would eventually become uniform, and it would eventually gel. So it will always gel because you're taking less and less particles to fill space. So no matter how few particles, if you go to the limit of the infinite system, you can always form a continuous uniform structure, uniform gel. So that's just this, and I didn't put it in. OK, let me continue on the theme then of colloidal gels and ask. So what I did here was, and I did this because he was correctly worried about, do they stick together? What could cause them to fall apart? And thermal energy is the thing that ultimately limits them. And we actually grew, these are the old days, we actually grew structures so that thermal energy would make them fall apart. The other thing, of course, that'll make them fall apart is gravity, right? Because they're buoyancy mismatch. And that's probably the more important thing. So to really prove that you could make something really huge, and we made them, I don't know, I think 6 orders of magnitude larger than the size of the particle, we actually turned gravity off. How do you do that? Exactly. I'll show you that in a minute. OK, so now I want to show you a practical example about gelation. And this is going to actually surprisingly relate back to something that you probably heard a lot about in this lecture. We were asked by a company that makes additives for motor oil. And every time you put motor oil in your car, you will use these additives, and it's actually a huge amount. And the reason is, first of all, this was like quite a while ago, like 15, 20 years ago. Secondly, the administration actually believed that the environment was important. Imagine that. And so what happened was, if you remember, have you ever seen a diesel engine not working properly? What's the first thing you think of a diesel engine not working properly? What do you think of? Soot coming out, black soot coming out. And so in those days, they were trying to improve the efficiency and the environmental performance of diesel engines without cheating by changing the program, right? Actually doing it properly. And so I won't go through all the details, but one of the things that they did was they said, we can produce more soot because we can filter that. So let's just run the engine in a condition where it produces more soot. And one of the things is it produces soot in the diesel oil, in the diesel fuel. And those are like, soot is like little carbon particles, little colloidal particles. It grows. How does it grow? It grows as a fractal. And what it does is it changes the viscosity of the oil. So they asked us, please, can we understand how to think about that? And basically, we showed that these things basically gel because they form these fractal clusters. And this is what it looks like. So if this is the soot, essentially, in the absence of any of this surfactant or dispersant. And if you increase the concentration, it starts forming this gel. If you change the amount of surfactant, this is actually increases in surfactant, you can take this and turn it into just the dispersion of particles. And similarly, you can take something like this and you can shear it. It's very viscous, but you can shear it and you can break it up. So what we did was we just went through a lot of careful experiments. I won't go through the details to determine what the volume fraction was. I won't go through the details. Also, we determined what the interaction energy was as a function of surfactant. But then we measured, knowing the volume fraction, we measured the rheological properties. So at the volume fractions, if they're low enough, you look at this and you see this is just as a function. Actually, you can see this function of volume fraction 0.48, 0.033, 0.048. So this is about 5%, 3%, 1%. This is the rheological properties. I've sort of hinted at this, but let me explain what we're doing. We're doing these oscillatory measurements. We're measuring the elastic and the viscous properties. This is the viscous property. You can see that it's growing linearly with frequency. That's because it's a viscosity. And it dominates. This is really fluid. So these things are all fluids. The particles are widely separated enough that they're fluid. But if you increase the volume fraction, so this is a 6.4, about 10, about 15%, you can see that they're really starting to form gels. And if you start measuring their rheological properties, this is now the elastic modulus. You can see the elastic modulus is much higher than the viscous modulus. This is really a solid. So if you do small oscillations, you see this is a solid. Here, there's some sort of crossover. Here, there's a crossover, but it's happening just about here. But you can take these data, and I take, for example, this set of data, and I just shift it. I just plot on a log-log plot. And then I just start sliding. And they scale with one another. Now, this is my experimentalist way of doing scaling, right? I'm plotting on a log-log plot. If I slide it either way, that's like multiplying it by some factor. Okay, I can take the same data and do the same thing here. Right? So I can take all these data. Right? This is really literally rheology of dirt, right? Dirt. And this is where I got that curve that I showed you. I can take all the data and I scale them all together. All I'm doing is I'm changing the volume fraction, and I'm looking at them. But so now I'm changing the frequency. I can only measure a certain frequency range, but I'm changing it to do this. So what's going on? Well, here's a simple way of understanding it. Remember, actually, if I told you, how do I think about this? I think about this as there's some elastic component. It's the gel that's giving me elasticity. But the gel, even at 15%, it's still 85% water or fluid, oil. So there's still, when I do this, I'm still making the oil. I'm having to move the oil, and that's like a viscous fluid. So there's always a viscous fluid there. As I go faster and faster, the viscosity, remember the response, the elastic response to, or the elasticity, the stresses that you measure when you do this go up as a function of frequency because it's a fluid. So it's always going up. So I can just imagine I have some solid part, the weak, this is really weak, this is a more rigid, and I have some fluid part. I just add them together. I just very naively add them together. Well, the volume fraction of the oil, the continuous phase, is not changing very much. So its contribution is more or less constant. But the volume fraction of this is changing quite a bit, the relative volume fraction, and it's getting more and more solid. So let me just say that if I just shift them along here, I just take this curve, for example, and shift it along here. I'm just shifting it along the viscosity. I'm shifting it linearly in both dimensions. Then it should just, this circle should match up with this, and everything should scale together. And so if you take the two scaling factors, those are the two amounts that I've scaled, and you plot one against the other, you in fact find that it's just linear. So that's just a simple reason. This kind of scaling is a simple reason why it exhibits that. And now you can do some more things. You can, because you can, if I go back here, well, back here, even though I can only measure this frequency range, I can determine where this crossover point is, and therefore I can determine the contribution of the elastic component, even though it's very weak. So now I can look really close. And remember, I showed you sometimes it was fluid, sometimes elastic. I plot the elastic modulus, the plateau modulus, as a function of volume fraction, and I see it fall off essentially to 0. At the same point, the viscosity, the effective viscosity that you measure in the fluid-like is increasing, and it has this characteristic behavior. Anytime you see something like that, you say, well, it's some kind of critical behavior. So you plot this on a log scale, but you subtract off this critical point, and you see something like this. So it's just saying that the elasticity is growing critically from some point. It's going from 0 at some critical crossover point. So I'm.
Can you tell us how omega star scales with time? There was omega star, right?
It was omega times A.
It was just omega times.
Yeah, that's times.
Oh,
Times. This is long time ago.
Okay.
We didn't know how to write times properly. Okay, I told you this. I won't go through all the details of the dispersion, but you can do the same thing with the dispersion. You actually make a scaling curve, and you can find a critical point in the same way. So as a function of dispersion, as a function of interaction energy, you can see where you lose the behavior. So now this is sort of looking as a function of interaction energy and volume fraction, and you cross over between a solid and a fluid. Well, you can do the same thing with shear. and you can measure the shear dependence, and you can measure a critical point, a critical shear. This is just showing that you can measure a critical shear. You can take these things where you're actually measuring, this is the yield stress, if you want, as a function of shear rate, and you can scale everything together. So you can do the same kind of scaling. So I'm going to skip a lot of this. But now, basically, you have this with interaction energy, with volume fraction, and you also can calculate a critical point in shear. So how do you plot this? Well, you plot this as a jamming diagram, right? Now you plot this as a function of inverse volume fraction, shear rate, and inverse energy. And this is the jamming behavior. So what's interesting is we did this because we read this commentary in, I think it was Nature, that Sid Nagel and Andrea Liu wrote about jamming. But they had drawn the jamming diagram like this. And we said, no, it has to be like this, just from based on experiment. This is the first experiment that actually showed that you could get jamming, and you could treat it in that way. And now, all the time when I see jamming diagrams, I don't follow it anymore, but when I always see it, it's drawn like this. So this is a really simple experiment, but you can actually see the importance of jamming in a real and experimental case in something that actually makes a difference. We showed this to the company that supports us. And what I like about this, we could publish it in a fancy journal and it gets a lot of citations, blah, blah, blah. But also now, when the company tries to design better surfactants, they ask, where does it jam? Where does it become solid? Let's measure rheological properties. They never did this before. So they qualitatively change the way they think, and really its impact, it has a huge impact on the way they design their surfactants or their dispersants. So that's sort of a fun way of doing things where, it really has a valuable use as well as being really cool science.
Should there be a jamming point on this?
We did this work maybe 10 years before people started talking about the J point, and I long ago stopped working in it, so I don't know. I have no idea. Okay. Let me talk a little bit more. This is about one type of essentially weak gelation, a weak colloidal gelation. Let me bring in a little bit more subtlety into this kind of gelation. So remember, I showed you there's this line here between a fluid and a solid. We call this the gel line, and it's not a universal line. It just depends on a lot of different things. But if I take colloidal particles and I make them attractive, then first thing that's going to happen before they gel, actually, is that if I make them attractive, they can undergo something like spinodal decomposition or binodal decomposition. They can phase separate into two regimes. There's nothing to stop you from doing that. And the way you would denote that is that there's some volume fraction. This is the energy, so the compared to kT. So the energy is increasing here. This is where it's right at kT. So this is the way the spinodal and the binodal will look like. But where this is located, there's an additional parameter in this, and that's the range of the interaction. So not only, since remember I showed you I can control the interaction by using this essentially purely repulsive interaction to induce attraction, that's the depletion interaction, and I can change the amount of interaction by changing the concentration of the depletant, and I can change the range of the interaction by changing the size of the depletant. So I can imagine now what happens as a function of range. Say if I change the range, what you see is that as you increase the range, as you decrease the range, this is this is short range, longer range. I make them longer and longer range. I shift the way where this actually behaves. So can we understand? I think I left a slide out here. Can we understand the nature of this spinodal and gelation behavior? And we really wanted to see, could we understand something about this spinodal decomposition? The problem with that is that this is relatively slow, and as you get to close to where you can really start to see these things, gravity really does play a role, and you have to avoid it. And in those days, the easiest way, now we're getting pretty good at index matching. In those days, the easiest way was just to do it in space. Of course, it helped that NASA would pay for the experiment if you did it in space, so that let us do it. But we actually did an experiment looking at this spinodal decomposition, going to space to do that. So this is a sample. This is I'm going to show you a movie. All we did was we took a sample and we mixed it up. These are colloidal particles with a very weak attractive interaction, and we mix them up and then we just image them as a function of time. If you were to do this on Earth, everything would just collapse to the bottom, but in space they don't. And so let me see, I think this is a movie. If I play it, this is just a series of images. And you see you get perfect spinodal decomposition, right? And perfect coarsening. You can see all kinds of cool things. Notice that there's always, around the edge, there's always particles. What does that say? Particles wet the side, right? They don't wet the surface, because you can see through it, but they wet the side. The side was made of a different material. But this, I'll play it again. This is really just looking at spinodal decomposition. And so you can analyze this, and you can compare it to all the theories, for the traditional theories for spinodal decomposition. Here's just a series. Oh, this is showing at the very end. These are several runs. At the very end, you see that it's really phase separated into colloid rich and colloid poor. That's what it has to do. It just keeps on coarsening. Okay, it's driven just by the coarsening dynamics of the interaction. So you can measure these things. You can measure the characteristic length scale. You can calculate the inverse of the length scale, the wave vector, and you can plot that as a function of time. And it follows exactly the theory for spinodal decomposition with hydrodynamic coarsening. And in fact, from this you can calculate what's the shortest length scale, what's the initial length scale that you start. And interestingly, it's the size of the particle. So the smallest length scale that starts to separate at is just, so it's basically dimers that start doing it. And then they start to coarsen, but they're coarsening in a way where there's essentially a surface tension that's keeping them together, right? So they're forming it's a weak surface tension, but there is a surface tension that has a boundary between the colloid rich and the colloid poor region. Okay, what about short-range interaction? How can we understand something about short-range interaction? Short-range interaction is where, okay, here, this one, you do clearly get a phase-separated region where essentially you get a gel. There's a solid connecting region of colloid-rich region that spans space. But the colloids are not really touching one another, or they're not very strongly interacting because the interaction energy is so weak. They're interacting, they're attractive, but they're not really solidly touching. What if we do the same kind of experiment, though, where they really touch? So I turn on a real strong interaction, and this is the sort of thing where now we can ask, are they self-supporting? Can they support one another? Let's at least understand the physics of what's happening there. What we did was we just looked at, now we can use, since doing these experiments, we couldn't do such sophisticated experiments in space. So instead what we did was we did the experiments on Earth by very, 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 very carefully buoyancy matching the particles to the solvent. Now, why this sounds simple, but the reason that it's not simple, why it sounds simple, because in principle what I can do is I can take the particles and I can put them, I can find two solvents that are good solvents for them, and I can find one solvent that's a little more dense and one solvent that's a little less dense, and I can just mix them till they exactly match, and I can test that by putting in the centrifuge and make sure that no matter how hard I centrifuge, I never do it. The problem is that I also want to study them with optical microscopy. And so I need not only the buoyancy to be matched, I need the index of refraction to be matched. I can do the same thing with two solvents to index match the index of refraction, but they're not going to be the same solvents. So to actually buoyancy match and index match, I need 3 solvents, and that gets to be a large phase space. Fortunately, a lot of people have been trying to do this, and now there are, in the lore of the colloid field, there are colloidal particles that you can both buoyancy and index match, so that you can do these experiments without suffering from gravitational effects. So we did an experiment where we added some of these depletants to induce an interaction between the particles, but we induced a relatively weak interaction, so they didn't form all the way to a gel. Let me see if I think I can show you. Well, no, I can't. They're weak enough that they want to gel, or they're coming close to gel, but they're not really at the point where they gel. And this is just, let's see if I can do this. This is just a snapshot, a 3-dimensional snapshot. And you can see the clusters of different sizes are colored by different amounts. If we increase the concentration of the depletant, then we can take that same sample and we can cause it to gel. In fact, here we're just showing the volume fraction. This is the concentration that of the depletant that we're adding, the polymer that we're adding. And we're right around here where it crosses between this is a gel and this is a fluid. We're right around here. Now we're just above this, and this is a gel. And let's see, yeah. So in fact, these you can see there are still thermal fluctuations. That's what you asked about. Are there thermal fluctuations? There are, but it's on average, it's still a gel. It's still a connected gel. This is a very weak gel because the interaction is pretty weak, but it's still a gel. So if we look, this is just taking a snapshot, and we look, this is the weak interaction. And you can see exactly what I was saying, that there are clusters that form. But if you watch any given cluster, it's not formed permanently, right? It exists and then it falls apart. It exists, falls apart. But I can take a snapshot of this, and I can calculate a cluster size distribution. I can calculate the number of clusters as a function of size in that snapshot. And this is for different concentrations of depletant. And the lines are basically simulations. So now we can go to people who do simulations and say, please simulate this and tell us what the interaction energy is. And you can do that because it turns out that in some simulations that Dan Frankel did a number of years ago that showed that the cluster mass distribution that you get doesn't depend sensitively on the shape of the interaction. So you can just do the simulation for a square interaction, so just a square well interaction. It's going to be the same as any of the other types of shapes, a Yukawa or a van der Waals type of shape. You see, you get exactly the same behavior. So we could just do the simulations for a simple square well interaction and calculate an effective attractive interaction between these. And then what we did was we measured, as a function of concentration, we showed that the interaction, here the interaction is, this is kT over the interaction energy, so this is decreasing. That means the interaction is getting stronger. And right at the point where we saw experimentally it gelled, that turned out to be right at the point where there's a bonodal or spinodal boundary of the system, where if you were to calculate that, and you do that for all of the data, they're exactly the same. So now actually we have we can understand a very simple picture of what's happening. If we look at the gelation as a function of time, these are the clusters. This is the growing cluster. This is the static structure factor. This is just scattering from this. Why I show that is if you look at it looks exactly like this. This static structure factor, if you want to interpret it, it's exactly the same static structure factor as spinodal decomposition. So what's happening is, as you start it, it's undergoing spinodal decomposition. But then it gels. So why does it gel? The reason it gels is that the clusters here are attractive enough, are solid enough, that they're jammed, that they're forming essentially a solid structure. They're forming, if you want, an attractive glass or jammed system. So the way to think of this is that the phase, this is more complicated, but the phase boundary, this is the volume fraction, this is the interaction energy, this is the gel point, this is the spinodal line. It actually goes to pretty concentrated and pretty dilute. Okay, this is very, very low concentration. This is concentration right around the glass transition, right around the jamming transition. And so what's happening is that you come up here and you undergo spinodal decomposition. Here you have very, very few particles. Here you have a high enough concentration that you're just jamming them together. So what that says is that a mechanism to understand colloidal gelation is that it's always driven by some attractive interaction. The thing that always drives it is spinodal decomposition. But then it phase separates into something where there are very few particles and something where there are very large particles. If that phase separated region can, if there's enough material that it can span space, then it's frozen into its location. It becomes dynamically frozen. It becomes a glass. And so that's the way you can understand the nature of colloidal gelation, understanding it from a very fundamental perspective. Okay, I showed another one. This is the same thing. I'm not going to. No, this is just showing the same thing. I thought I could. So in fact, I'll give you a choice. I wasn't sure. I looked at how much I had before, and there's still. I can stay for another 25 minutes. I have one other topic that I can talk about, but maybe before I do that, let me give you a chance to ask questions. So just in general, I'm going to tell you, everything I've showed you is more historic. I'm going to show you some stuff that's much more recent about some of the colloid stuff. Another reason that you can use colloidal particles. I'd like to do that, but it'll take about 20 minutes. So before I do that, just to make sure there's time, does anybody have any questions that they'd like to ask about anything that I've talked about or anything else? You don't have to. I can just keep going and talking. I'll give you a chance. Yes?
This example with one particle gelating to the whole space, can you explain
Can I what?
it again? How can one particle do that whole space?
The reason is that the way to think about this is that as you grow the cluster, its density is decreasing. The bigger I make it, the lower the density. Right. So here, the cluster size obviously doesn't fill space. It's just one. But as I start growing them, then even though I'm taking 4 of these things and I'm making a cluster with 4, so my total volume is increased by 4, my volume of the particle is actually increased by more than that. It's filling more space because the density is decreasing. So now I keep increasing the mass, and the density is decreasing, so the amount of volume it takes is increasing larger. So the relative volume that it takes gets larger and larger. Another way of saying it is that here, this is a solid particle. 2 is a dimer. If I got this chain, now I've got lots of empty space in the inside. I'm making these real chain-like structures which extend over much larger volume. And that just grows more and more. So eventually, I fill space, but I have very, very little material to do that.
But not just one particle, but 4 particles.
Yeah, because I fooled you by talking about a finite experiment, 1 particle in this room. But I really am thinking about an infinite system. And then it can always gel.
Is it fair to say what you're saying is 1 particle obviously can't fill 1 room, but a billion particles could span a billion rooms?
Yes. Yes. Exactly right. Exactly right. So you have to, the right way of answering the question is not to do it in a finite volume, but to do it in an infinite volume, and then it's always going to gel. Pardon? At lower density, yes. Yes, yes. Well, no, sorry. At the point it gels, then up until that critical crossover radius, it's not a constant density, it's a fractal density, right? So it's very dilute. After that, the density is constant. If I take, up to, if a billion rooms cause it to gel, and I take 10 billion rooms on length scales larger than the 1 billion, it's going to be constant. Any other questions? Okay, so the last thing I wanted to talk about is something a very, very simple thing, but it's really, the reason to tell you about this is that I've tried to present to you a broad picture of colloids. This is colloids experiments 1 and 1, right? So this is still 1. But what's really, as physicists, what's one of the really super cool things that we can do with colloids? What's one of the really interesting things that we do? The interesting thing is that they're this beautiful model for looking at statistical physics, at looking at phase behavior. And everything I've told you until now is really looking at things that are absolutely important for colloidal, the uses of colloidal particles. It's colloidal physics, but it's really much more for understanding things that are very practical. There's another side that is very, very intriguing and very valuable, and that's you can use colloidal systems to model more traditional solids. So I have a colleague, Franz Papen, who is one of the really pioneers in understanding glasses, metallic glasses, traditional glass transitions. This goes way back before all the fancy theories that we talk about now. It's just the free volume theory. He was really a big proponent of that. This is ancient work that he's done, but he's just studied. I mean, he knows more about glasses than all of us put together, I guarantee you. And even if you work on glasses, I still will make that claim. But he now has moved almost entirely to doing colloid experiments because you can study the behavior of materials using colloids in a way you can't do with normal materials. They still have these phase behavior. It's not perfect, but it's pretty good because a lot of the times, not always, but a lot of the times, the thing that dictates the phase behavior of a normal solid, okay, there's a lot of things about the specific quantum mechanical ordering, how you bond, but still, what really ultimately dictates things is the volume and how it packs. And that you can model with colloids just as well. So you can't exactly model things, but you can learn a great deal by using colloidal particles to model real systems. And the nice thing is that now with modern microscopy, you can see the individual particles and you can follow their motion in time. So here we asked a really super simple question. We said, how does a crystal melt? If you have a crystal, how does it melt? How does it go from a solid into a liquid, into a fluid? So actually, Arjun Yode, using colloidal particles, did some beautiful experiments, and he showed, not surprisingly, that if you look at colloidal crystals, so now you can just find something that has a phase boundary between a liquid and a solid, and you just ask, how do you see it melt? And so he did this. He did a really clever experiment, as he always does, where he took particles that you can change the size just by changing the temperature. So you can change the effective volume fraction. So you can go from a region where they're crystalline to a region where they're liquid. And he showed that the melting always occurs at interfaces, at grain boundaries. You always get melting there. So melting always occurs at an interface between a fluid and a solid. And this is not surprising. This is exactly what you would expect. If you have a crystal and ask how it melts, it just melts from the surface. The surface just starts to melt and fall away. So that's what you expect. That's what you see. But you can ask the question, what happens if there aren't any interfaces? How can it melt? Actually, that's a question that Born asked, the same Born who did quantum mechanics. Born asked that question, I think in 1938 or something. And he predicted that if there are no interfaces, then you basically, it's sort of like you can heat it higher and higher and higher, and then eventually it's going to undergo some elastic catastrophe. It's just going to fall apart. So this is just a prediction of Born that was, 80 years old or something. And how can you prove it? Or how can you test it? Well, you can do it with simulation. But how can you do it in a real system? Well, you can do that with colloids quite nicely. And I showed you sort of how you can do it. If you take particles that are slightly repulsive and you put them together and you increase the volume, you'll get them to crystallize. But they're crystallizing not because they're an attraction, but because they're a repulsion, and you're controlling the volume. You're bringing them closer and closer and closer together until they feel the interaction. So this is a relatively high volume fraction. I can decrease the volume fraction. If you look carefully, you'll see this is actually a movie. You can see the fluctuations. If I go to really low volume fractions, they're still crystalline, but you can see they're really fluctuating. So you can do this very nicely with colloids. This is actually a Wigner lattice. So Wigner first predicted for electrons that you can make a lattice, that's a crystal. He was thinking about two-dimensional systems. You can make a two-dimensional crystal of electrons, which are repulsive, just by squeezing them together. So you're basically constraining them in a volume. Here these particles are constrained in a volume, and they form a crystal lattice. So it's a repulsive crystal, but it's still a crystal. Now, yes?
In Wigner crystal, it requires the interaction is much stronger than the kinetic energy.
So?
But here you are at the boundary of melting, so your kinetic energy is comparable to the interaction.
Yeah, but it's still stronger because it's not melting. These are.
But the Wigner crystal requires much stronger. The repulsive interaction dominates over the kinetic energy.
Now make it so it's closer and closer to the point where it melts. How does it melt? How does it melt?
To me, I don't think near the melting point the kinetic energy is small enough to regard it as a Wigner crystal.
So it's going to go to a fluid, right? Tell me how it does it. That's all I'm asking. So you've answered. You've posed the question in your own language, but you've posed exactly the question I want to answer. Okay, so we can do these experiments now, and so what we do is we don't change the temperature, we change the volume fraction, right? That changes the separation, that changes how close, how strong the interaction is. So if I go back here and just look at this, you see that here there's one type, there's another type. Oh, these movies aren't playing anymore. There's another type, but sorry for the movies, it's a problem with the computer, but these things will move, they'll fluctuate. Before you could see them fluctuating, but they stay in their crystal lattice. So you can actually look at this and you can do all the experiments you want. You change the volume fraction. Here's high volume fraction. You look at the lattice, their crystals. You can do the scattering. You can measure the structure factor. This, it turns out, is FCC. This is BCC, so it's actually a transition between FCC and BCC. And that's actually a well-known transition. One of the oldest theories about the behavior of melting says that all FCC lattices should first go to BCC before they melt. And there are a lot of metals that actually do that. And the reason is that the BCC lattice is much closer to a liquid structure than a FCC lattice. Here is a fluid, so you can see this. Here you can actually see there's a small region where it looks like there's coexistence between a crystal and a liquid, and you can do the liquid You do the scattering from the liquid, you see this, what's in the liquid, you do the scattering from the solid. When I say scattering, obviously we're not doing scattering, we're just calculating the scattering factor because you know the positions. You do the same thing, you see it's the same as the BCC. Okay, you can measure these things. I won't go through the details. You can calculate the, yes, sir?
So SCC is on the surface to the liquid.
I'm sorry?
SCC is in the bulk and BCC is on the powder.
No, because we can't adjust we can only adjust the concentration or the volume fraction. And so if we go to high volume fractions, that's really strongly interacting, then it's FCC. If you go to low volume fractions, still a solid, it transitions between FCC and BCC. And if you go all the way to melting, it stays BCC and then eventually melts.
At the boundary level.
Yeah. Yeah. You can measure the mean square displacement of the particles. Here, this is looking at increasing volume fractions, therefore increasing interactions. Here's where it's a fluid, so the particles diffuse freely. Fluid, this is where, right between the liquid and the solid, the particles still move, right? But they stay in a lattice, so they're pinned. So their mean square displacement doesn't increase in time. They're still fluctuating, but they're fluctuating around this. And this is really a permanent lattice. So another thing you can do is you can measure the amplitude. Just where it starts to melt, you can measure the amplitude of the fluctuations. That tells you how much the particle is fluctuating around its crystal lattice. It's still in a crystal, but it's fluctuating around the lattice. And so you can normalize that by the lattice constant. And that's called the Lindemann parameter. So the rule of thumb is that materials melt when the Lindemann parameter becomes 10%. Right? Just the rule. And it's just a rule of thumb. Here, these are the Lindemann. What's this? This is the Lindemann parameter. The Lindemann parameter that the average Lindemann parameter of the particles until they melt. This is volume fraction. This is where they melt. Notice what it is. It goes up to about 0.25. So what does that say? That says that the average fluctuations are enormous. They're still crystalline, but they're enormous. And the reason for this is you're just preventing melting. You're making the particles hotter and hotter. So they're fluctuating more and more, but you're not allowing them to melt because there's no interface. So here shows that the Lindemann parameter, when it melts, is getting really high.
So what's on the x-axis, like the volume fraction? Or
Yes.
Like
Yes.
Volume fraction of
Yes, this is a volume fraction.
5%?
Yes, because these are repulsive particles, so they're not the hard spheres, right? So they want to repel one another. You're just squeezing them down, even though they're repulsive. So the volume fraction is not the same crystallization fraction. Okay, and this depends on the charge.
Sure.
Does that make this then a superheated solid?
Exactly. Exactly right. This makes exactly right. This makes it a superheated solid. And so, in fact, don't tell me I lost some part. Oh, dear. I put these in, and I'm gonna be really angry if I. Okay, guys. There's enough time. You're going to have to bear with me. I forgot to throw in some slides. I'm going to see if I can do it. So bear with me for 30 seconds, because there's one really super important thing that I wanted to show you that's not here. I apologize. I copied a bunch of slides, but I forgot to copy these. So what you can do is look at all those particles. Now, since you've defined, you see that the Lindemann criteria where they melt is 25%. You can look at the individual particles, the Lindemann criteria, the Lindemann parameter for the individual particles. And some of them will be actually hotter than 25%. They'll be superheated even more. There's a distribution. So if you just plot the number of particles with, or if you plot those particles with Lindemann parameters greater than the melting, you see that as the volume fraction gets closer and closer to melting, the number of particles that are even hotter, so they're essentially melted, they're still sitting on the lattice, but they're just fluctuating more and more and more. The number of particles are growing, but moreover, they're strongly correlated. So those hot particles, here they're random, but there's a lot of clusters of hot particles. And as you get closer and closer to melting, you see these clusters of hot particles. And ultimately when it melts. So how do you understand this? Well, now you have these clusters, and so these are the clusters that are melting. So this gives you some intuition about what melting really is. You're forming these superheated particles that are having these clusters that can extend across the sample. Eventually the whole sample can start to melt by having these superheated particles extend across them. And so you can look at how they're correlated. You can measure their structure. Not surprisingly, they're fractal. They have to because they have to spread and fill space.
So is this experiment quasi-2D or is it 3D?
It's not. That's just one of the limitations of confocal microscopy. You can't see so far. If you want to have high resolution, you have a relatively low working distance. So you're limited by your working distance.
So you're taking a slice out of the 3D?
Yes. It's a slice of a 3D. And I'd like to make it thicker, but you can't do it with the resolution that you have. So they're fractal clusters. They're, you can calculate the mass, cluster mass distribution. It's like an exponential with, sorry, it's a power law with an exponential cutoff. The power law is about -2. And you see this scaling behavior. So here, this is just measuring the mass as a function of the reduced volume fraction. And you see a scaling behavior. You see a scaling behavior in the size of the clusters. You see a scaling behavior if you just do a measure of the elastic constant. You see a scaling behavior. So basically, you see all these scaling behaviors. You see something that has a power law dependence as it melts. But wait a minute. If I have a scaling behavior, that's a second-order transition, right? I see fluctuation. The nature of a second-order transition is there are fluctuations, so I know where that transition is, even if I'm not there, just by measuring the fluctuations. So I can see that here. I know how close I am to melting just by looking at these power laws. But what do we know about melting? It's a first-order phase transition. Not only that, I showed you it was first-order because I showed you there was a coexistence. But it's a very weakly first-order transition. What we're doing is we're preventing melting, so we're superheating it. So you get right to the point where it melts before it actually melts. So the difference between the liquid and the solid gets weaker and weaker and weaker. So it has a lot of character of a second-order phase transition, but it's really still a first-order phase transition. So that's what Born melting is. That's the catastrophe of Born melting. I won't. We did some, or one of the co-authors did some theory. I think I won't go through all the details. There's some subtlety about understanding the elastic constant. If you just do linear elastic theory, it doesn't work. You have to do nonlinear elastic theory because the fluctuations are so large. The motion locally is not affine. But the critical thing here, the beautiful thing here is that you can actually see melting in what's almost the damn closest you'll ever come to seeing melting of a liquid, a solid to a liquid, that's almost second order. It's not quite, but it's almost second order. It's very, very close. So it's very, very weakly first order, and that's because this is where you're preventing melting. You're killing all the interfaces. Okay, I'll skip all this. Just blah blah. That's the end. there's time for 1 or 2 questions. And I showed you my phone number if you have more, if you think of things. Any questions?